Good morning, everyone, and welcome to Carla 2021 Latin America High Performance Computing Conference. On behalf of Carla 2021, I hope you have a very nice day. And with this, we can now start the activities of the day. We commence now with the opening ceremony. And to do this, I give floor to our first moderator, Salma Jalife, President of Centro México Digital.
Muchas gracias. Es para mí un gran placer en representación de nuestro comité organizador y como secretaria de SCALAC, el darle la bienvenida a nuestras autoridades de la Universidad de Guadalajara y de Carla, así como a nuestra audiencia, a la Conferencia Internacional Carla 2021 que se lleva a cabo en la ciudad de Guadalajara, Jalisco, México, y virtualmente en el resto del mundo. Estamos muy agradecidos con la Universidad de Guadalajara por su apoyo incondicional y que nos ha provisto como anfitrión en la organización, y también agradezco a las instituciones que han organizado este evento para conformar un programa tan rico como el que vemos hoy. Carla es una conferencia internacional que busca proveer un foro para fortalecer y dar crecimiento al cómputo de alto desempeño en la comunidad latinoamericana a través del intercambio y la diseminación de nuevas ideas, técnicas e investigación en HPC y aplicaciones en diferentes áreas. En estos 7 años de su existencia, Carla se ha convertido en el líder de la conferencia de cómputo de alto desempeño en esta región. Hemos invitado a la comunidad internacional para que comparta sus avances tanto en HPC como en la convergencia entre HPC e inteligencia artificial. En esas áreas, que estas dos áreas se han convertido en una máquina predominante de la innovación y del desarrollo de esta cuarta revolución industrial. Con esto en mente, déjenme hacer una parada en este momento y referirme a los magníficos tutoriales y talleres que se llevaron a cabo la semana pasada y en los primeros 2 días de esta semana, donde excedimos las expectativas de nuestra comunidad y participaron más de 800 personas de 22 países. Regresando a esta ceremonia de apertura, quiero compartirles que vamos a tener keynote speakers e invitados conferencistas que se han localizado a lo largo de la agenda de esta conferencia para debatir y resaltar los temas importantes y las tendencias y prácticas actuales de HPC y AI y las materias relacionadas con estos temas. También somos afortunados de tener el apoyo de un cuadro de sponsors que ustedes van a encontrar virtualmente durante las pláticas que les han sido asignadas. Para fortalecer la cooperación y encontrar formas de sostenibilidad, estamos buscando 2 paneles internacionales con iniciativas regionales y con autoridades de distintas organizaciones internacionales que por lo general realizan políticas públicas y regulación, quienes van a acompañarnos también en esta conferencia. Espero sinceramente que disfruten hoy y los próximos 2 días el debate y el enlace virtual que vamos a tener en el diálogo e intercambio entre los ponentes y la audiencia, y les agradezco a todos por su participación. En este momento le quiero introducir a nuestros distinguidos autoridades de la ceremonia de apertura, y primero le daré la palabra al maestro Gustavo Padilla, rector del Centro Universitario de Ciencias Económicas Administrativas, CUSEA de UDG, de la Universidad de Guadalajara, y vicepresidente de Carla 2021. Maestro Gustavo Padilla, tiene la palabra.
Muchas gracias, Salma Jalife, por esta introducción y en particular por el trabajo que bajo su liderazgo se está realizando en esta iniciativa del Centro México Digital. También saludar a las autoridades que nos acompañan en esta mañana, a la maestra Guadalupe Cid Escobedo, quien coordina a nombre de la universidad, del rector general de la universidad, todos los servicios de infraestructura tecnológica que se han venido fortaleciendo, digamos, en las, yo diría que en las últimas 2 décadas, a nivel de tecnologías de información y el uso del supercómputo en los últimos años ha sido estratégico para el desarrollo de las funciones sustantivas de una universidad como la Universidad de Guadalajara. También saludo a Carla Ostov, espero pronunciar bien. Saludo a la doctora por todo el trabajo que hace este Laboratorio Nacional de Computación Científica, que son fundamentales para poder ir hacia el desarrollo. Al doctor Isidro también, director del Centro de Investigación y Estudios Avanzados del Instituto Politécnico Nacional, y quien, por cierto, preside este cuerpo de especialistas que nos hemos reunido a lo largo de varias años en una conferencia tan importante como lo es Carla. Y ahora, bueno, siendo 2021, esta organización tiene su sede en México y particularmente con la participación de la Universidad de Guadalajara, nos parece muy, muy relevante. Yo quiero en términos generales hacer una primera gran reflexión sobre el tema, no sin antes felicitar y agradecer todo el trabajo realizado por todos los equipos que hicieron posible esta conferencia, esta reunión, a Lisette Robles en particular, quien dirige el Centro de Supercómputo de la Universidad de Guadalajara, y a todas y a todos. Bueno, déjenme decirles que si hay algo que a un servidor como académico, con una experiencia en la función pública, en el ámbito federal, en el ámbito estatal, y como un promotor del desarrollo de las políticas públicas y del desarrollo de nuestra sociedad con inclusión y con equidad, si hay algo que para mí es de pasión y es de mayor interés profesional, es precisamente lo que está sucediendo en el mundo con todas las tecnologías exponenciales. Ahora ya no hablamos nada más de tecnologías, estamos hablando de organizaciones exponenciales. Y cuando hablamos de organizaciones exponenciales, cuando hablamos de tecnologías que pueden ser disruptivas, que pueden transformar en segundos un problema global en una solución, debemos de entender, debemos de reconocer y debemos de advertir que estamos en un momentum importantísimo en la historia de la humanidad. A mí, créanme lo que me queda muy claro, ¿no? Que el supercómputo y que la inteligencia artificial, todo el proceso de pensamiento de máquina, el rol que está jugando hoy el machine learning en nuestra sociedad y particularmente la inteligencia artificial, estamos al borde de un mundo que todavía no conocemos. Yo he sido un seguidor, ¿no?, de todas las tendencias que en el mundo se han desarrollado, visitando hubs ¿no? He visto lo que está haciendo Israel, por ejemplo, en el uso de la ciencia y el uso de la tecnología al servicio de la humanidad. Yo estoy cierto que tenemos dos grandes retos. Por un lado, sí seguir avanzando en el supercómputo, sí seguir aprovechando las oportunidades, sí alentar el uso de la inteligencia artificial con todos los dilemas que se nos están presentando. Uno de ellos tiene que ver hasta dónde la parte ética del uso de los datos, el uso de la información, hasta dónde vamos a permitir como humanidad que los robots nos reemplacen o sustituyan roles y rutinas y actividades que le son propias al ser humano, y la parte ética, la parte de las brechas de desigualdad que se están haciendo en todo el planeta por no entender, ¿no?, que la tecnología es un medio y no es un fin en sí mismo. Estamos al borde de un momento muy serio para la humanidad. Estamos empezando a ver la luz de una pandemia que nos dejó, nos sacudió a nivel global. No estábamos preparados para atender esta crisis provocada por una pandemia y además por otra serie de problemáticas. Así que yo estoy un convencido, como rector del principal centro universitario de la Universidad de Guadalajara, que puede hacer análisis económico y de desarrollo de la tecnología, como un centro universitario preocupado por el desarrollo armónico de la sociedad, que esta incursión de nuestra sociedad a una sociedad digital, además, de hecho tenemos el gusto de que en CUSEA tenemos pues una serie de capacidades en materia de tecnologías de información, economía y desarrollo centrado, y recientemente creamos un centro para la sociedad digital, donde precisamente invitamos a una experta que recientemente acaba de terminar su periodo en el BID en Chile, representante del BID Chile, y quien estuvo a cargo de la estrategia digital nacional en años previos. Salma, me gustaría mucho tener mucha comunicación con ustedes. Yolanda Martínez se integró, es una egresada de CUSEA, de la Universidad de Guadalajara, porque nos interesa muchísimo, junto con Lisette y con todo el equipo que está en torno al supercómputo. Tenemos el centro de innovación en ciudades inteligentes con el doctor Víctor Larios, que está viendo el futuro de las ciudades y todo lo que está sucediendo. Perdón que me extienda. Me dijeron que fuera muy corto, pero no puedo acortar lo que para mí es relevante. En CUSEA nos hemos propuesto transformar al centro en un Smart Campus, en un campus que utilice la inteligencia artificial, ¿no?, que aproveche la humanidad, que aproveche nuestra generación. Tenemos el gran riesgo, y con esto yo termino, de que o nos subimos en una ola democrática y de valores y de derecho a esta oportunidad global, o nos quedamos fuera de la ola, o nos revolcará la ola como país. Así que desde la Universidad de Guadalajara y desde el CUSEA, todo el apoyo a este trabajo. Me da mucho gusto ser parte de esta conferencia y sobre todo más ser parte del board organizador. Y yo quiero de veras decirles a toda la audiencia que ojalá y sigan de cerca, escuchar con todo interés los keynote speakers que van a hablar sobre los retos y desafíos del supercómputo y la inteligencia artificial, y de nuestros invitados, porque seguramente vamos a sacar de este espacio grandes reflexiones, una conclusión y una agenda de trabajo muy fuerte por realizar el futuro. Así que, pues, enhorabuena, nos da mucho gusto, les deseamos lo mejor y vamos a estar al pendiente de los trabajos. Muy buenos días y muchas gracias.
Muchísimas gracias, maestro Padilla. Para nosotros es muy importante las palabras que ha dicho, sobre todo el que la ciencia esté al servicio de la humanidad y que vayamos construyendo desde cada uno de nuestros nichos esta economía digital, pero con ética y buscando la inclusión de todas las partes. Muchísimas gracias. Doy ahora la palabra a la maestra Guadalupe Cid, coordinadora general de Servicios Administrativos e Infraestructura Tecnológica del CGSAIT de la Universidad de Guadalajara. Bienvenida, maestra Cid.
Muchas gracias, Alma. Estimados directivos, investigadores, estudiantes y amigos que hoy nos acompañan, muy buenos días. Sean todos bienvenidos a la 8ª edición, primera en Guadalajara, de Carla, la conferencia de cómputo de alto rendimiento en Latinoamérica, que hoy tiene lugar, aunque remotamente, pero en esencia, en nuestra querida casa de estudio, particularmente en el Centro Universitario de Ciencias Económico-Administrativas CUSEA, un espacio que honra la generación de ideas disruptivas y el gran interés de su rector, el maestro Gustavo Padilla Montes, y de su profesorado por compartir y transformar el conocimiento entre nuestros jóvenes estudiantes. Y parte de lo que hoy nos tiene aquí es precisamente eso, compartir el conocimiento, aprender el procesamiento de grandes volúmenes de datos en este evento internacional y multidisciplinar como es Carla. Desde hace 3 años, con la apertura del Centro de Análisis de Datos y Supercómputo CATS, la Universidad de Guadalajara se ha desempeñado en fortalecer el desarrollo de la ciencia y la tecnología mediante el uso del supercómputo, y este es un gran avance tecnológico protagonista de esta transformación digital que hoy vivimos. Históricamente, el cómputo ha significado para la humanidad un bastión de desarrollo científico. En pleno siglo XXI, una computadora es capaz de procesar datos con una exactitud y rapidez tal que obtenemos a cambio información valiosísima. Ni qué decir de una supercomputadora o computadora de alto rendimiento con una capacidad extraordinaria de procesamiento y almacenamiento que puede ser utilizado tanto para el estudio del modelado molecular de enfermedades como para el estudio profundo del universo. Desde luego, esta innovadora y poderosa tecnología no se concentra solo en ámbitos académicos, sino que además está revolucionando las tecnologías con las cuales se está basando. Tenemos presente que al hablar de cómputo de alto rendimiento, debemos hablar también de inteligencia artificial, 2 áreas claves, como bien lo dice la edición de este año de Carla, motor predominante de la innovación y del desarrollo. Toda la industria que está regida a nivel de datos requiere este tipo de procesamiento. Por ello, es un beneplácito compartirles que en esta edición podemos conocer los proyectos que la Universidad de Guadalajara está impulsando. Como institución de educación superior, es nuestro deber habilitar la infraestructura que nos beneficiará a todos para sumarle y potenciar la investigación en México. Derivado de ello es que dicha jornada, como parte de una iniciativa por seguir promoviendo el supercómputo en nuestro país, en América Latina, en el mundo, estará conformada por un ciclo de conferencias magistrales, workshops y talleres que buscan ser un espacio de reflexión para generar y compartir ideas a través de los diálogos que establezcamos. Por ello es tan importante la participación de nuestros investigadores en estos eventos. Confío en que una vez concluida esta jornada, dirijamos los esfuerzos a potencializar nuestros proyectos de investigación mediante las bondades del supercómputo, pues esta tecnología es fundamental para impulsar el desarrollo de un país, de nuestro país. Y de ahí la relevancia de esta conferencia en nuestra ciudad, de que hoy ustedes sean los actores de esta transformación por la que transitamos. Sin más, espero que el contenido temático preparado les sea de provecho y me permito agradecer una vez más a nuestras autoridades universitarias y a nuestras instituciones hermanas en el ámbito nacional e internacional, en espera de que esta jornada de trabajo resulte en un nuevo conocimiento. Sean todos y todas bienvenidos. Gracias.
Muchísimas gracias, maestra Cid. Es para nosotros un placer saber que va a estar presente la Universidad de Guadalajara a través de la presentación de sus proyectos, y eso pues releva e incentiva a que se potencie la investigación, y sobre todo en temas tan importantes como la industria de los datos, que es útil no solo para la academia, para la industria, para el gobierno y para la toma de decisiones importantes y la solución de problemas. Muchísimas gracias por sus palabras. Le doy ahora la palabra a la doctora Carla Ostov, coordinadora del CEPAD-COTIC, Laboratorio Nacional de Computación Científica, el LNCC. Adelante, Carla.
Muchas gracias. Voy a hablar en inglés. First of all, I would like to thank Dr. Isidoro for the invitation. As a researcher in HPC from the National Laboratory for Scientific Computing in Brazil, coordinator of the National High Performance Programming Center, coordinator of the High Performance Processing Service, and Santos Dumont Supercomputer Steering Committee member, I'm very proud to be a part of such an important conference for the development of HPC in Latin America and Caribbean. The Santos Dumont supercomputer has the power of 5.1 petaflops and is the most powerful supercomputer dedicated for the research community in Latin America and Caribbean. The supercomputer is now running almost 300 research projects from 28 research areas. And I would like to give you the information that a leader from a Santos Dumont project has to be a member from a Brazilian research institute or university, but any project can have international collaborators. And you can find all details in Santos Dumont webpage. Like most countries in the world, Latin America and Caribbean countries are now facing a strong economic crisis. And on the other hand, international problems from interdisciplinary research areas such as climate change and COVID-19 are demanding a huge effort from the research community. Therefore, international collaborations are paramount in such a difficult time, and we must work to improve international collaborations. Initiatives such as America HPC collaboration that integrate efforts in a community to reach achievements supported by HPC, or Red Clara that fosters collaboration and development for education, science, and innovation, and SCALAC that organizes and integrates strategic infrastructure that include HPC, scientific computing, and HCC for the Latin America and Caribbean region are important initiatives for Latin American and Caribbean countries. And I would like to take this opportunity to invite all of you to join these communities and to be part from these initiatives. So I would like to thank one more time Dr. Isidoro for this opportunity and hope you enjoy the conference. Desejo a todos uma boa conferência. Muito obrigada.
Muchas gracias, Carla. No mencionaste algo muy importante que tú haces, que es promover el que las mujeres estén en HPC. Eres una fuerte promotora de mujeres en HPC y quiero resaltarlo para que ustedes sepan que no ha sido una tarea fácil, pero ya tenemos muchísimas mujeres participando en este en esta temática que naturalmente ha sido de hombres. Carla, qué bueno que mencionaste la colaboración. Vamos a tener un panel de colaboración, pero es importante resaltar lo que dijiste de la integración continental que estamos buscando con Estados Unidos y Canadá, América Latina y el Caribe, y sobre todo la interconectividad que nos presenta Red Clara con la red de alta velocidad. Y SCALAC, que se crea en 2013 para poder fortalecer estas actividades de HPC y cómputo científico. Muchísimas gracias por tus palabras y ahora le doy la palabra al doctor Isidoro Gittler, presidente de Carla 2021 y director de Abacus, Centro de Investigación, del Centro de Investigación y Estudios Avanzados del Instituto Politécnico Nacional. Buenos días, Isidoro.
Buenos días. Muchísimas gracias, Alma. Distinguidos miembros del Presidium, distinguidos miembros del Comité Organizador de Carla, distinguidos miembros del Comité Local de Carla, distinguidos ponentes plenarios e invitados, queridos ponentes de conferencias y talleres, queridos instructores de los tutoriales, distinguidos patrocinadores, colegas, participantes, estudiantes, queridos amigos. Bienvenidos todos a Carla 2021, la octava edición de la Conferencia Latinoamericana de Computación de Alto Rendimiento. Bienvenidos, queridos expositores plenarios e invitados. Esperamos con interés sus conocimientos sobre las fronteras de la supercomputación. Welcome all to Carla 2021, the 8th edition of the Latin America High Performance Computing Conference. Welcome, dear keynote and invited speakers. We await with interest your insight about the frontiers of supercomputing. Sabemos que la inversión en ciencia y tecnología, la construcción de infraestructura avanzada, la atracción y formación de recursos humanos altamente capacitados y la generación de conocimiento de vanguardia en las áreas de computación avanzada, computación científica y computación de alto rendimiento constituyen una base sólida para entender, abordar y resolver muchas preguntas desafiantes asociadas a problemas complejos que se presentan en las más diversas áreas del conocimiento y cuyo estudio en general genera oportunidades para mejorar nuestra calidad de vida. Por ejemplo, predecir oportunamente y con precisión el clima, entender el cambio climático global, prevenir desastres naturales, dilucidar algunos de los misterios que plantean las ciencias biológicas, optimizar el tráfico terrestre o aéreo, diseñar nuevas moléculas para uso médico, consultar nuevos materiales con diversos usos, explorar el uso de energías alternativas, entender nuestro universo, por citar solo algunas. Durante la conferencia escucharemos en varias pláticas cómo la era de la computación exaescala está a la vuelta de la esquina. En América Latina es necesario, yo diría urgente, crear una masa crítica de recursos humanos, redes de colaboración de infraestructura computacional y supervías de conectividad. La colaboración es la mejor estrategia y en ese sentido hay que insistir en proyectos regionales de cooperación latinoamericana que permitan que los centros de supercomputación existentes colaboren entre sí y ofrezcan de manera racional y colectiva sus servicios a los centros de investigación y a las universidades para fortalecer su columna vertebral académica y de investigación. Confiamos que este foro sirva para arrojar luz, para discernir entre los posibles caminos a seguir. Nuestro objetivo es proporcionar un foro de clase mundial para el intercambio y la difusión de nuevas ideas, investigaciones y técnicas de computación de alto rendimiento. En otras palabras, estamos aquí reunidos para intercambiar, discutir y explorar juntos los horizontes a medio y largo plazo de esta inquietante área del conocimiento moderno. Quiero expresar mi reconocimiento y gratitud a la Universidad de Guadalajara, nuestro distinguido anfitrión, así como a CUDI, la Corporación Universitaria para el Desarrollo de Internet, nuestro distinguido anfitrión de Internet. Juntos han formado un equipo logístico que ha sido increíblemente solidario, eficiente, amable y servicial. Sin ellos, no hay duda, esta conferencia no hubiera sido posible. Gracias a las autoridades de la Universidad de Guadalajara, Gustavo Padilla Montes, rector Centro Universitario de Ciencias Económicas y Administrativas de la UDG, y María Guadalupe Cid Escobedo, coordinadora general de Servicios Administrativos e Infraestructura Tecnológica de la UDG. Gracias al director general de CUDI, Carlos Casasús López Hermosa. Gracias a Scalac y a Red Clara. Quiero expresar mi gratitud y reconocimiento al equipo de logística, sin los cuales esta reunión hubiera sido imposible. Por la UDG, tenemos claramente que reconocer a Lisette Robles Dueñas, responsable del Centro de Análisis de Datos y Supercómputo, y su equipo de apoyo, Marco Antonio Sierra, Webmaster, y a todo el equipo de UDG, Angie Fernández, Eud Velasco, Adrián Velasco, Iván Toledano. Por CUDI, ¿qué podemos decir sin el apoyo de Marta Ávila, coordinadora de comunicación, a Quetzali Chávez Aguilar, contadora, y a Eduardo Romero Solís, de producción? Por Sinvestar, yo no podría simplemente funcionar sin el apoyo de Estela Hernández Juárez y el equipo de Abacus. Por Red Clara, a Tania Altamirano, gerente de Relaciones Académicas. Por CEDIA, a Claudio Chacón Arévalo. Por el CNS del IPCIT, a Jessica Mendiola Fuentes, responsable del HPC de CNS. A los miembros de Scalac y algunos miembros de la Red Mexicana de Supercómputo. Agradezco sincera y profundamente a todo el comité organizador de Carla 2021. Son el alma que da vitalidad a esta conferencia. Agradezco el esfuerzo y trabajo de todos los chairs del Board Committee, coordinadores de cada actividad realizada en Carla 2021, por su tiempo, compañerismo, disposición y dedicación. En especial mi gratitud a Carlos Jaime Barrios por su invaluable apoyo e ilimitada paciencia. Agradezco profundamente a nuestros patrocinadores platino, NVIDIA, Red Hat y Hewlett Packard Enterprise, cuyo apoyo ha sido fundamental para la realización de Carla 2021. Esperamos que nuestra colaboración siga creciendo en los próximos años. Agradezco sinceramente a todos los demás patrocinadores del sector privado, en especial a Alter y a todas las instituciones educativas que nos han apoyado. Por último, quiero dar las gracias a nuestros más de 800 participantes, que son la razón de ser, el corazón de esta reunión. Esperemos, y sinceramente lo deseo, que estas charlas y esta conferencia nos lleven un paso más allá en el entendimiento del futuro del cómputo de alto rendimiento. Muchas gracias.
Muchísimas gracias, Isidoro. Ahora quiero, pues has tocado un tema importante, la inversión en ciencia y tecnología. Esperamos que con este panel de autoridades podamos nosotros buscar esta sostenibilidad que tanto requiere la región. Tú mencionaste, necesitamos crear una masa crítica de infraestructuras, tanto de redes de telecomunicaciones como de cómputo de alto desempeño y las aplicaciones, y por lo tanto ojalá que haya una luz muy clara en este sentido para la sostenibilidad de nuestra región y para apoyar todos estos proyectos que requieren respuestas a las necesidades que tenemos hoy en día, sobre todo de cambio climático y de salud. Quisiera dar la palabra a quien va a dar la inauguración, a dar por declarada la inauguración de este evento, para que siendo las 9:31 lo haga, por favor. Va a ser el...
Siendo las 9:30. Perdón.
Ser tú, ¿verdad?
Sí, siendo las 9:30 de la mañana del día 6 de octubre del 2021, declaro a la conferencia Carla 2021 formalmente inaugurada. Muchísimas gracias y comenzamos el día de nuestras actividades.
Muchas gracias. Agradezco a las autoridades de la Universidad de Guadalajara y de Carla 2021 por haber estado en esta ceremonia de inauguración, y regreso la palabra al maestro de ceremonias para que continuemos con nuestro programa. Muchísimas gracias a todos por su asistencia.
Gracias y mucho éxito. Y vamos a un aplauso ahí para... Gracias.
Gracias a ustedes. Muchísimas gracias.
Okay. Great talk. We thank you for your attention, and we invite you to stay connected. We now continue with our keynote presentation, presented by Professor Satoshi Matsuoka, entitled Fukaku, the first exascale supercomputer, accelerator, simulation, AI, and big data to transform the society for sustainability and beyond. And to introduce our keynote speaker, I now give the floor to Isidoro Gittler.
Thank you very much. Dear Professor Satoshi Matsuoka, it is an honor and pleasure to have the opportunity to introduce such distinguished scholar and renowned computer scientist. Let me very briefly share with our audience some of your achievements. Professor Matsuoka completed all his studies in information science from bachelor to PhD degree at the University of Tokyo in Japan. He had professional appointments in the University of Tokyo, Tokyo Institute of Technology, Global Scientific Information and Computing Center at the Tokyo Institute of Technology, National Institute of Technology, and RIKEN Advanced Institute for Computational Science, among several others. On April 2018, he was appointed as the new director of RIKEN, Center for Computational Science, where he oversees the development of the Fukaku, aka post-K projected task with building the successor of the K computer. He has written over 5,000 articles and chaired many of the ACM IEEE conferences. He is a fellow of the ACM and the European ISC and has won among awards, many awards, including the Japan Society for the Promotion of Science Prize in 2005, awarded by His Highness Prince Akishino, the ACM Gordon Bell Prize in 2011, the IEEE Computer Science Sydney Fernbach Memorial Award 214, given to him for his work on software systems for high-performance computing on advanced infrastructural platforms, large-scale supercomputer, and heterogeneous GPU-CPU supercomputers. The HPC Wire 2015 Reader's Choice Awards Outstanding Leadership in HPC, co-award with Professor Jack Tongara. Some of his research activities, in his own words, are: my research is principally in system software for large-scale supercomputers and similar infrastructures such as clouds for HPC, and more recently, convergence of big data and AI with HPC, as well as investigating the post-Moore technologies towards 2025. Over the years, I have been involved and led a number of large collaborative projects that worked on basic elements that are now significant for the current and, more importantly, future exascale system, such as fault tolerance, low power, strong scalability, programmability, as well as large-scale I/O. Some of the major projects I have led are Tsubame-2, which became the fourth fastest supercomputer in the world at the greenest production supercomputer in the world on the Green 500 2 consecutive times, heavily utilizing GPUs and other power-efficient technologies. More recent, the billion wave fault tolerance in supercomputers, which investigates the key technologies for reliable exascale in supercomputing. The Ultra Green Supercomputing and its successor Post-Green project, where we investigate low power control and cooling technologies to achieve exascale power requirements. The most recent result being design and construction of oil-immersed Tsubame KFC supercomputer that became #1 in the world on the Green 500 2 consecutive editions. And the extreme big data, where we aim to converge HPC, AI, and big data technologies in order to be able to handle extreme scale data that can be only processed with supercomputing. Finally, he states, we're starting research on post-Moore technologies, where we claim that transition from flops-centric means of computer acceleration will be replaced by data or byte-centric computing. And as such, the convergence of HPC and big data AI are more fundamental, not just because of mutual needs. Dear Professor Matsuoka, I really do not want to consume any more of your valuable time. Please, Professor Matsuoka, we are eager to listen to your keynote talk titled Fukaku, the first exascale supercomputer accelerating simulation, AI, and big data to transform the society for sustainability and beyond. The floor is yours.
Well, thank you very much for many kind words. And I'm very honored to be able to speak to you as a keynote speaker for this very notable conference in Latin America. Of course, I wish that I could be there in person, but of course the situation, the global situation, prevents me from doing this. Fortunately, we have wonderful technology to be able to allow me to deliver this keynote. The only technology we haven't solved is the fact that the world is spherical. So the time zone difference, there's nothing we can do about except to stay up late. But I'm really honored and happy to deliver this keynote. So so is the slide showing? I just want to do a technical check. Is the slide showing on your screens?
Yes, it is okay.
Okay, thank you. Okay, so today's talk will be mainly on Fukaku, but of course, Fukaku, on one hand, is a crystallization of many of the work that has been kindly mentioned, of course, not just by me, but many of my collaborators and colleagues. And also, Fukaku is also a project involving, it's a national project involving hundreds of thousands of people. And I'm very honored to represent the project, and also very happy to represent my center, to which I am appointed a director. So I'll talk a little bit about my center currently. So the weekend is, as many may know, it's the premier national lab of Japan. The European equivalent will be like Max Planck. In fact, I think it's very similar. With Riken and Max Planck are very similar as institutes, and we know we have lots of people doing very different branches of science and technology. There are 13 centers in Riken, and our Riken RCCS, or Center for Computational Science, is one of the centers. 13 centers. There are also other centers for informatics, centers on AI. There's a new center established in quantum computing, and of course there are other centers on bio materials, etc., and nuclear physics, and etc., etc. At my center, we basically, on the research also as a flagship national center for HPC research. So on one hand, we're one of the Riken centers, but also a national center on HPC research. Not just not just do the stewardship of Fukaku. So we do considerable research in HPC, or computing, and we say science of computing, by computing, and for computing. Science of computing is computer science. We study computing as a scientific discipline. Science by computing is using the immense power afforded by our studies to other branches of science. And science for computing is working with other branches of science that would benefit computing, like quantum, for example. And so collectively, the trilateral collaborations of all three areas, or synergies, we are investigating on all fronts to advance computing. So we have many research teams. We have about almost 30. Will be almost 30 teams in a few months, and as you can see, there are many people, many team leaders. Some are also professors at universities, and we are as a HPC center. We're one of the world's leading center dedicated to HPC. Now about Fukaku. But one of our other mission, of course, not just to individual research, but also to research, develop, and operate the national flagship machine, the supercomputer of Japan. And the current machine is Fukaku. Now, Fukaku is another name for Mount Fuji. It's usually called Fujisan, meaning Mount Fuji, but Fukaku is an alternative name. And the reason we named Fukaku as Fukaku is the fact that this Mount Fuji, is of course our national symbolic national mountain, but also signifies our idealism of what supercomputers should be. On one hand, Mount Fuji, of course, is the highest mountain in Japan, has a very high peak. So this represents the leading performance. But also, we want the machine, unlike traditional Japanese supercomputers that have only catered to very narrow sets of applications and research scientists, our goal in this modern days of age of IT, where high performance computing is basically disseminated and penetrating all branches of computing and everywhere, we really need our computing technology to proliferate to a very broad audience. So as such, the machine is our leading machine should also be very broad. Broad meaning broad user base, broad applicability to different types of disciplines, broad applications, etc. And also not just for traditional simulation, but also data science, AI, and so forth. And so all these, so this broadness and also high peak, the simultaneous satisfaction of both properties is basically is our ideal. But of course, one can imagine that it's easy to say will that satisfy both requirements at the same time. Usually it's hard, but it's usually hard to do. It's easy to make a machine that's very specialized, accelerated certain sets, very narrow sets of applications. And it's not easy, but it's much easier than building a general purpose machine that's fast everywhere. And so the converse is true. You can build a general purpose machine using general purpose CPU, but then they are usually not as performant as those that are more specialized. So how do we build a machine that's on one hand very fast, but also very general purpose? It's technologically very hard. So it became a big R&D challenge for us and for Japan. And so that's why it was a national project. So the government made tremendous investments as risk money into the research and development and facilitation of the machine. And then designated RIKEN and also our partner Fujitsu as the development partnership. And then, of course, our task was not only to build the machine, but also to facilitate it and, of course, operate it as a national resource. But it wasn't just RIKEN and Fujitsu. Basically, as you see on the right-hand side corner below, basically, it involved the entire Japanese HPC community, the application people, computer science people, not just with RIKEN, but just throughout, not just in academia, but also part industry, not just Fujitsu, but all the partners, and so forth, many national labs. So it was a sort of all community effort, and this is sort of synonymous to the Moonshot project. Moonshot is where the United States in of course 1960s, President John F. Kennedy made a speech saying, "Well, we'll go to the moon for 10 years," and then the entire aeronautics space industry of the United States got together under NASA, many contractors, researchers, and so forth, and worked together to formulate a big national project to send a man to the moon, which they were successful. And this Fukaku, of course, is not at that scale, but very, very similar in spirit. That basically we set this enormously high goal, which is unattainable if we were left to just one company, making a product. Rather, it had to be a real, a national effort. And the resulting machine Fukaku, of course, that's how we'll describe, became number one. And but it became number one in many aspects because on one hand, we really targeted broad ranges of applications, not just targeting on a singleton benchmark. And also we put all the we have lots of high-risk technologies that either we developed or we adopted we put into the chip and other aspects of the system, which are still not available in any other machines or any other chips. So this, for example, this new S4FX chip, co-designed by Fujitsu and us, is about three times more performant compared to other mainstream CPUs, of course, if the application is tuned properly, or 3 times more power efficient compared to, let's say, mainstream Xeons or AMD's general purpose CPUs. And of course, it has also accelerations for other workloads such as AI and also big data. So put this, and Fukaku consists of 160,000 of these chips, and then the total compute capacity of Fukaku, is equivalent to about 20 million smartphones. Well, why do we compare to smartphones? Because it runs the same code. Because A2FX is also an ARM is an ARM processor, and it understands the ARM instruction set. It's fully compatible with your smartphone processor. Of course, the internal microarchitecture is completely different, but it runs the same code. And 20 million smartphones is about the same number of smartphones that are shipped in Japan annually. So that means if we have 2 or 3 Fukakus around, that'll basically be equivalent to the entire national computing capacity requirements of Japan. So Fukaku is a machine of that magnitude. But of course, as I said, Fukaku was not designed to excel at benchmarks. In fact, the broadness, oops, something happened. Yeah, the broadness is largely attributed to looking at, basically the co-design with real applications. And these applications, of course, have been identified running on the predecessor machine, the K computer, or other supercomputers by various research teams in Japan. And also they covered subject matters that are of national importance, especially those pertaining to sustainability goals. So sustainability goals like health, medicine, environment, disaster, energy, carbon neutrality, materials manufacturing, and of course we have basic sciences too. Basically, these areas have been identified, what science and applications were required, and of course these developments of these applications that are that will do the science as well as run very efficiently on Fukaku was co-designed and co-developed alongside the hardware and software development. And the goal was basically, the entire project goal was to basically be about 100 times faster, well, at least 2 orders of magnitude faster than the K computer, the predecessor K computer, and some applications exceeding this 2 orders of magnitude speed up, meaning more than 100 times faster compared to the K computer, which was a pretty fast machine, was number 1 in 2011. So it was a very high goal. And so some of the applications are just massive, not the one, molecular dynamics, not the one you see on the left-hand side, like a singleton protein, but a group of proteins like this that are in the real cellular environment with the billions of atoms. Or so the Nobel Prize was awarded to the climate science, and one of the awardees were a Japanese scientist who's in the United States, but a Japanese scientist who really innovated the climate science. And of course, K computer and now the success of Fukaku is really doing sub-kilometer both weather and climate simulation capabilities. But of course, we can do this on the K, but we can never integrate over 100 years. So Fukaku was really necessary in order to advance the climate science. And also other co-design target, the modification of this was with weather simulation, but with weather, obviously you need to do a data simulation with the observation in real time. So this is a big data type of workload along with simulation. So this was also became a big goal to be able to do real-time weather prediction with a very large data simulation at something like 30-second intervals, and that involved, again, 100 times speed up over what we had observed in K. So Fukaku was developed over the course of about 10 years. In fact, over 10 years. The first conception of Fukaku began with various people, including me, back in 2010. And this was just before K was launched. So K was being installed, developed and manufactured, is being installed at the time, but still wasn't there as a machine. So but technologically K was pretty much done. So a group of us got together and started really thinking about, okay, what do we do with the next generation exascale machine? And then many things followed, and I won't go into details of every aspect of the project, but just to give you a brief summary. So we wrote a white paper, we did some preparation, what's called a feasibility study project. 2014, based on these projects, the project was approved, Fukaku, the post-K project was officially approved by the government. And then we spent 5 years designing and building a machine, and about 4 years, we had the first chip with many difficulties. And then 2019, we got the final version of the chip, and the production started on the Fukaku, rest of the Fukaku, the cabinets and networks and so forth. We started installation at the Recon site, and then 2020, basically the machine was fully built, but of course we had to do software and other things, pre-production preparation. And finally, March of 2021, Fukaku began operation. So it's been in operation for about 6 months now. Very busy machine. So what are the innovations we realized? Well, Fukaku, basically, the reason why we have this biggest and fastest machine in the world, not just fastest in terms of benchmark, but also excelling in the applications, is that, of course, the machine has lots of leadership technologies, and either we developed or we adopted, and so forth. So I already talked about the CPU a bit. It's the first server CPU built with 7nm technology. As I said, it's about 3 times faster. It's very power efficient, but also very fast. One of the reasons why it's fast is it's the first general purpose CPU to use HBM2, and it's still the only, I think, mainstream CPU to use HBM2. HBM2 is only used in GPUs or some other very specialized processors, but not on a general purpose processor yet. A4FX is the only processor that uses HBM2. And we get about terabyte of bandwidth as a result. But also, it's not just the CPU and memory interconnect. So each node of Fukaku has the TOFU D interconnect. Tofu is tofu, it's white bean curd. It's called tofu because it's a 6-dimensional torus topology. It looks like, when we draw it, it looks like tofu. So, but tofu. So every processor, every CPU chip has an embedded network. So unlike other machines where the network is a separate card attached to an I/O bus, with Fukaku, the network is embedded. And this is one of the reasons. So Fukaku scales to 160,000 nodes, completely switchless, external switchless, because switch is embedded. All the network switches, not just the SCAs, network interface, but also the network switch is totally embedded within a chip, just like the old BlueGene machine with IBM. So we get about essentially 160,000 nodes, but we also have 160,000 network switches, or about 1.6 million network ports. And so this gives about 6 petabytes per second of injection bandwidth, which is very fast, about 10 times faster than all the data centers in the world combined, including those by Google, Amazon, and so forth. And I won't go into disaggregated architecture, yes, but it's also from an architectural standpoint, it's a disaggregated architecture. Okay, so this is a chip, and there have been many publications about X4FX. I won't really go into details, but you see the overview here. It's a new processor. It's ARM compliant, but it has a new scale vector extension for vector processing. The microarchitecture is, of course, entirely our own. We didn't get any microarchitecture license from ARM. because we have a better one. But of course, the instruction set's compliant. So we work considerably, especially the new instruction architecture, but also to be compliant totally with the other ARM standards, not just ISA. These are specs, but high-level overview of A2FX is sort of like this. So on one hand, it's a mini-core ARM CPU. So it has 48 compute cores plus up to 4 assistant cores for offloading operating system tasks and so forth, interrupts and so forth, to eliminate system noise. And each core is not as fast as Intel, although of course compared to something like Xeon Phi, it's a lot faster. And so it's not bad. It's like the older Xeon in terms of each core performance and the integer and so forth. So on one hand, you can look at this chip as a mini-core ARM processor. But at the same time, it's a streaming processor or vector processor, very much like the classic vector machine or the modern day GPUs. It's not that it has a separate GPU, doesn't have a separate GPU, but each core sort of acts like a stream processor, just like a GPU streaming processor. So it has a very wide vector, but not only that, it supports memory streaming enhancing features architecturally, including the memory subsystem, in order to achieve very high bandwidth, and also things like barrier synchronization. So we get the best of both worlds. On one hand, you can program this chip like a CPU, but also you get GPU-like performance while still sticking to a standard programming model. So this is internal, but I won't go into details. But one thing you might notice is, of course, you get 256 gigabytes per second per HBM2 channel, and we have 4 channels. We get 1 terabyte per second of memory bandwidth. We do extensive power management on the chip, and that's why it's one of the reasons why it's so power efficient. But also we can control the power usage explicitly, not just clocking, not just doing things like frequency and voltage adjustments, but we can, but at the user level, we can physically turn the execution units off or detune the chip, or in case this such things like clock gating certain units when it doesn't affect your performance. For example, when you have a memory bandwidth bound application, it's not very useful to have a whole bunch of ALUs consuming power, so you might as well shut them down. And you can do that with A2FX. Also, when you have a 160,000 node system, reliability, fault tolerance becomes a very important issue. Of course, we have lots of software artifacts, software resiliency artifacts at the system and software level. We have, for example, we support Veloce, which is the outgrowth of some of the work my student and I had done back in 2011. Sort of, it goes back way back then. But and then adopted by the Europeans and made into a real system, which we now sort of back and board it back to Fukaku. But fundamentally, this because it was built by Fujitsu, the chip was designed principally by Fujitsu, of course. It has a RAS design, which is basically mainframe grade. So Fujitsu's been making mainframes for 50 years, so they're very, very good at that. So so that's one thing when people neglect when they say, "Oh, we have this wonderful chip, which is really performant." Well, for a single node, yes, but when you build a real scalable supercomputer, exascale supercomputer, obviously you need you need a very, very high resiliency, and the baseline resiliency at the chip level with these mainframe RAS features will be essential. So on simple benchmark like Himeno, which is a very simple Poisson solver, compared to Intel, because this benchmark is so memory bandwidth bound, we get several times performance gain over Xeons. In fact, this is 2 Xeon chips on a single node, a dual socket node. So on a socket-to-socket basis, we're about 8 times faster. Now, of course, this is the best case, and usually it's more like 3 to 4 times faster. And it all favorably to other, more dedicated vector processors like the NEC or the Tesla GPUs. And this is not just with these small benchmarks. For some of the more popular open source applications, we also see quite a bit of advantage. So this is power efficiency difference. We also have charts for absolute performance, but they're by and large the same. So if you compare socket to socket, so we show you the power efficiency here. And as you can see across the board, be it memory bandwidth bound like OpenFOAM or StackFM3D or VRF, or being more compute bound like Ab Initio, we are basically across the board, we are about 3 times more power efficient as compared to a high-end Xeon processor. And as I said, the chip also embeds the TOFU interconnect, and that's one of the reasons why it's performed but also power efficient, because the interconnect and also the switch being embedded into the chip, we only use about 8 to 9 watts out of the 25 millimeter die area consumed by the interconnect. So so that's about 4 to 5% of the node power consumption. So it's a very small fraction as compared to things like, let's say, EDR, HDR, InfiniBand, or things like 100 gigabit Ethernet, where it's more like 25, 30 watts per port. So, and also this allows us to connect the interface directly to the on-chip Taurus network, and then no I/O bus, intervening I/O bus. So we get very fast performance, especially in terms of latency. In fact, we can do things like cache injection quite easily. So I won't go into too much details, but basically the latency, the minimum latency between the nodes and like MPI ping pong is about half a microsecond. And also the injection bandwidth is about 40 gigabytes per second, which is by and large equivalent to a 400 gigabit network per node. So this is how it's packaged. We get 2 chips per what's called a CMU, which is a dual node board, not dual socket node, but dual board. So these are 2 nodes in a single board. You can see it's entirely liquid cooled. Although, AC4FX is not a high power consuming chip. On maximum, use about 200 watts, including the HBM. It's because HBM is also, just like GPUs, it's embedded. But unlike GPUs, like that use like 400 watts, this is more like a 200 watt chip. And you can see this is stacked in a rack in a very dense manner. And so on each rack, we get 384 nodes, which is basically a petaflop rack. And then there are about 432 racks, or 158,176 nodes. Then this is about twice the number of nodes compared to a K computer. In fact, in terms of number of nodes, also it's the largest supercomputer ever built, superseding the Sequoia in the old days, by losing out Sequoia at Livermore in the US. And theoretical peak performance, you see, many numbers, but basically on some of the precision, and double precision, we're about half exaflop. And single precision or lower precision like FP16, we easily exceed an exaflop. And also, more importantly, the theoretical peak memory bandwidth is 163 petabytes per second, which is several times larger than any other supercomputer in the world. And this is evident in the raw benchmarks, not just the top 500, but also benchmarks like HPCG, which is entirely memory bound, or HPLAI, which is is a deep learning convolutional network, neural network proxy, and also a Graph 500, which is, of course, you do graph searches. And across the board, we are about 2 times to over 5 times faster than the number 2 machines, and we've been doing that for the past 3 consecutive editions. Next one, maybe for some of the benchmarks like the top 500, maybe the US or Chinese machine may supersede us, but yeah, that's fine. We still, there are other benchmarks, and of course, no machine stays on the top forever. But we're quite proud of our achievements in being able to not only be number 1, but number 1 across the board, and number 1 by by tremendous margins over the number 2 machine. And of course, it was very important to be very broad. Like I said, originally with Fukaku, and we need to cover many application portfolios, and in fact, if we had only excelled on the top 500, then the project would have been a complete failure. If we were like number 1 in the top 500, but did not perform well on other benchmarks or towards the applications, then of course, the project's a total failure. Because, if the machine is good at a broad range of applications, by all means, it should be very performant across the board on benchmarks too. That's a natural consequence. So we're very happy that we excelled in many benchmarks, including the 4 I've shown you, the ranking benchmarks. And this really signifies that we had built a machine with not only high peak, but also very broad applicability, as I told you at the very beginning of the talk. And of course, the real goal, as I said, was not to do well on the benchmarks, but to satisfy the R&D goals. And very happy to tell you that across the, it kind of varies between applications. Some are in the 20x, but some are 131x. So, and the average is about 70x across the board. So we're very happy with the results. And this kind of we're working very hard to allow these kinds of speed up to be achieved on other applications. This results translate to other applications. Of course, it's not always easy because we always have to optimize, to the new hardware. We have to have the right compilers and libraries and so forth. So as I speak, and even some of our teams are having a conversation with the folks at the people at DOE, because they're using Fukaku or to port their code and running into performance problems, and that we're working to solve those for their benchmarks and applications for the coding teams. But this is a very good sign that we fundamentally have a very performant machine across the board. And of course, we don't just build a machine as a single instance. Fujitsu's intention to commercialize it. We have 2 types of machines. One is the same as Fukaku, the scale out, liquid cooled cabinet, but the other is a commodity one, air cooled, standard, 19-inch rack type server with 8 nodes in 1U. I'm sorry, 2U. And and this uses InfiniBand, this network, not Tofu. And also Cray, or now HPE, also sells a version of the machine with A2FX. It's the first time that an American company had sold a Japanese-made CPU embedded into their own machine and also ran their software stack. And so we're very proud of this achievement. And of course, they're very happy about this too. And this is and so the machine not only has made it to various parts of Japan, but also it's been sold. A2FX has been sold worldwide to many institutions. And one reason why people like this, of course, performance, but also the generality. In fact, if you look at the software stack that we have implemented on Fukaku, some are still in the works, but this is mostly what's working. So on one hand, we have a traditional HPC software stack like Fortran and math libraries and so forth. But also we have this support for this software stack pertaining to clouds and big data, deep learning, things like containers and so forth. And of course, we run Red Hat Linux out of the box, no patches or anything. You know, the ARM version of Red Hat Linux just runs out of the box, and that's what we run. And also work with DOE to support our software packaging using their SPAC tool that they developed. So a lot of these working with DOE to get a lot of their utilities and applications that are already SPACified onto our machine. So, you know, basically, so Fukaku sort of encompasses the traditional HPC, but also AI, big data, and cloud software stacks in a single machine. And this synergy has been fairly straightforward, in fact, although there are some work we have to do. So, and this is really the modern HPC that we really synergize all these workloads with not only amongst themselves, but also with the rest of the IT industry. So, you know, a lot of these open source software just run right out of the box, or about some of the more performance conscious ones, for example, like Julia, or like one API with one DNN, and so forth. We work with their development team to optimize the code for H4FX/ARM. And also, Fujitsu is working with the commercial vendors, many ISVs, to port very popular ISV software onto ARM SVE, especially tuned for H4FX. Because even now, currently, although there will be many ARM chips that will be coming in the next few years supporting SVE, right now, at this moment, H4FX is still the only chip that supports SVE in hardware. So ARM's H4FX has become a development target for these commercial applications. And like I said, we not only support traditional like batch style HPC usage, but considerable cloud software stack support across our user for all our users. So not just for select, we don't have a cloud partition or anything like that. It's just Fukaku. If a user would use Fukaku, he has all the cloud features available to him, just like AWS or Azure, and so forth. So you can use the traditional interface like batch queues, or you can use the cloud interface to interact with Fukaku. And using that feature, we're working with various partners, commercial partners that are basically value-add type of companies, like Rescale or Altair, or some of the Japanese domestic companies like Linus or HPC Systems and so forth. So basically, they have their services, cloud services built on top of cloud APIs, and they would use like EC2, Amazon EC2 as a backend. So we're working with them to make Fukaku the backend for them. So some of these are already in service. So people who are companies that want to use Fukaku, they can use, but if they're clients to these high-end services, they can use the familiar web interface. But instead of submitting to EC2, they will be, their job will be processed on Fukaku, and it'll be much faster. And so since we started production in March, so the usage, the job fill for the basically the usage ratio is been climbing steadily to the point where in September 90% there's not over 90% utilization, which is pretty amazing when you come to think about it. We have 158,000 nodes, about 160,000 nodes, and people are using more than 90% of that. So so it's a very heavily used, so in a matter of months after we started official production. Of course, the machine was always busy in pre-production, but we opened it up to very select sets of users who had high-end workloads. Now it's open to all the users, including international ones. So you can apply to Fukaku, actually, to use Fukaku. But basically, it's a very, very busy machine. And you take Exascale. I remember, 10, 15 years ago when there was international meetings to talk about exascale. A lot of people, there were a lot of claims from the audience saying, I mean, even if we had an exascale machine, how do we, we can't fill the capacity, or what application run at exascale? Well, 10, 15 years later, we do have an exascale machine, Fukaku, and it's filled up, and we do have applications, important ones that scale to the entire machine. So the average power has been about approximately 20 megawatts, because things average out if you run under normal circumstances. If you run particular applications like a benchmark, full system benchmark, of course, the system may use more power, up to 42 megawatts for the entire site, or about 35 megawatts for the entire machine. But because there's a huge power swing, because of Fukaku, because of the power efficiency nature of Fukaku. So on the average, we're using about 20 megawatts. So DOE, the US DOE basically said, they would want to build a machine by about 2020. The target was to achieve a exascale machine with 20 megawatts. So Fukaku is not limited to 20 megawatt exaflop, but operationally it performs as an exascale machine. And on the average, we get about 20 megawatts. We use about 20 megawatts. So the DOE, so basically we had achieved the DOE goal of exascale at 20 megawatts before anyone else. So Fukaku is being used, like I said, by normal users, but also there are some priority users, and there are many application areas with focused application areas. Of course, you can also apply with your own ideas, but there are some programs that particularly aim for high-end delivery of results, and these are usually pertaining to, again, sustainability goals, like health, solving cancer, whole brain simulation, earthquake, disaster prevention, drug discovery, atmosphere, climate, carbon neutrality, new energy source, new battery technologies, et cetera, et cetera, et cetera. So many important applications are being run on Fukaku to achieve to advance our society. So one particular example, when Fukaku was being deployed initially, that was beginning of late 2019 and beginning of 2020, and we all remember, and that's the reason I'm doing this remotely, and that's COVID. That's when COVID started. So we quickly realized that we had to deal with COVID. So we had to many things in order to cope with COVID. We had lots of problems with the supply chain. We had problems with people possibly getting infected and disrupting the installation, and all of these problems. So we cope with that with Fujitsu. But also it gave us the opportunity to really think about, can we use our supercomputing power, not just the machine itself, but all the applications and sciences and applications, and of course software and systems that we have been developing. Can we repurpose them to fight COVID? So we created a program with our Ministry of MEXT, and had a call and issued a call where we would say, well, we have this Fukaku, it's in test mode, still it's in pre-production mode, but we can make each, if you apply and get accepted, there's a potential you'll get resource that will be pretty much equivalent to one of the top tier supercomputers, all to yourself or your project. But in order to solve COVID, so you got to have a good plan to solve COVID with that immense compute. Of course, we're not going to give you the entire Fukaku, but each of these projects would receive compute resource over the course of the year that would be equivalent to like second or third fastest machine in Japan, which are pretty fast. And there were 6 projects in the end that were accepted. So these are not like standard COVID, where people only dedicate very small parts of the machine to COVID, but this is huge huge resource being allocated to COVID. So 6 of them. And so it went from anywhere from very microscopic first principles investigation of a virus as of course, as a at atomic or even quantum levels. For example, to investigate how the bonding, what's the exact mechanism of strong bonding by these new strains, and their exact bonding forces. To things like pharmaceutical, trying to repurpose drugs, see what they're effective, but thousands of drugs. But also to societal epidemiological investigations, like and because we all know now that most of the COVID is transferred through dominant transmission mode is aerosols or effectively air infection, not by touching or stuff, but basically by air. So someone coughs or speaks, you inhale the aerosols, you get infected. But what are the public situation? Was are masks effective? So nobody had a credible scientific answer, really. And in fact, computer simulation had not been applied extensively to these epidemiological studies. So we had, and it was for a very good reason. But we overcame the difficulties, and we now have. So Japan basically has fairly low number of COVID cases for internationally, without going into full lockdown mode, because we're constitutionally not possible to have lockdowns. But despite that, the infection rates have been fairly low, and it's somewhere attributed to Fukaku, because everybody knows Fukaku from our simulations of anti-COVID. I'll show you in a second, but in my rainy times. Yeah. So we did things like drug discovery. I'll skip that, but we have very good drug candidates, but that is very computationally intensive. I like to try to use the rest of my time to talk about the Droplet Aerosol. This is principally work being done by Makoto Tsukura, who's one of our team leaders, but also professor at Kobe University. And also I contribute this work too. So basically COVID-19 is transmitted through aerosols and droplets, and in fact aerosols, but aerosols are very difficult to simulate. As you can see, it's comes out of your mouth when you cough or you speak or you sing or something like that. And as they travel through the air, the heavy particles will drop onto the floor or stick to your clothing. But as it travels, it dries up and becomes aerosol, or it's aerosol in the first place. And once it becomes an aerosol, it floats in the air for a very sustainable amount of time. Like, in fact, it could stay afloat for hours. And the reason the team was able to do this innovative simulations of aerosol, because it's a very complicated geometry you have to deal with. You have to generate these geometries rapidly. You have to be very exact. And the team was basically doing industrial CFD, things like not only cars, but very complex turbine combustions, city airflows. In fact, one particular simulation they were doing is internal combustion engine and the fuel injector. And they noticed when they were looking at how COVID-19 was spread, they said, well, hey, this person coughing and the aerosols and droplets dispersed through the atmosphere. That's exactly like fuel injection in its internal combustion engine. It's the same physics, and we can deal with that. It's a hard problem, but we can deal with that because we have the methods and also an application to do it, and we can run it on Fukaku because the code is tuned on Fukaku. Although it's very heavy, it's very expensive code. It's heavily parallelized in Fukaku. It can be parallelized to the tens of thousands of nodes, because we have to run complex codes like these turbine engines. So maybe we can deal with the problem. So they went on to transform these studies onto aerosol infection studies. And I won't really go into the details of their methods, but basically it's a finite volume, highly structured finite volume method, but also they have many innovations to deal with very complicated geometries. Because, for example, they have to deal with, when they do the analysis of infections of, let's say, running vehicles, when you open the door, you have to simulate the door panes, which are really thin. If you know CFD, that's very difficult for these irregular grid type of simulations. But so you go to unstructured grids, it's even hard for unstructured grids, even if you use AMR. But meshing becomes the big issue. You can't really generate these credible meshes in minutes from the CAD geometry. So basically, there are all these problems, but they've been able to resolve, basically prioritizing the industrial usage, which really helped to create the essentially digital twins of the societal situations for to deal with infection. So, so these are the governing equation. You have the drag, evaporation, wall reflection, not just the standard mesh and the Lagrange particle solvers, but all these effects of the particle behavior. Also, to get the initial conditions, they work with epidemiological experimentalists to get initial conditions as to how the fabric, how the aerosols are ejected under various conditions, like people wearing masks and so forth. Of course, they can do mass deformation. This is done by FEM. But they can also simulated mass deformation through FEM, or even. And so combining all these methods, they were able to analyze mass, because if you all remember, the very early stages of the pandemic, organizations like WHO and even CDC, US CDC said, well, masks may not be that effective, so don't wear them. So it's not recommended people wear them all the time. Yeah, right. So of course, yeah, right. Yes, that doesn't make sense. But we had no counter argument. So basically went and simulated, and of course found the masks to be extremely effective and also very dependent on the materials. So, and non-woven, of course, N95 masks are the best, but non-woven masks are pretty good. We also saw the effect of these particles being ejected out of the gaps that may be caused by the loosely fitting masks. And so that's the very early result. But of course, it's not just the masks. We did face shields. Then we worked with many companies to scale the simulation to not just to a single person with a mask, but to vehicles with like trains with tons of people inside in a crowded train, like a commuter train in Japan, or things like auditoriums, or like Olympic stadiums. And we work with many companies, construction companies, airlines, even companies like Boeing, Toyota, etc. We work with ministries. So basically, over the course of a year, we created digital twins of many of these societal situations, and we're able to basically, as the infection rates would be going up, but will be going down, there'll be new risks because the society will be relaxed. So then we say, well, what are the new risks? Well, maybe people will want to resume going to the karaoke, but what are the risks? How do aerosols disperse in karaoke? Especially with ventilation, what would the effect? What about the restaurants? What about people may start traveling again? What about taxis? So taxis are very complicated because it's not just the standard CFD like when in typical vehicle design where you have only simulate the skin, that is the exterior of the vehicle, in order to do complete airflow analysis. Not only you have to do the analysis of the complicated geometry inside the cabin, but also the engine room. We simulate the entire airflow in the engine room and other parts of the vehicle, and also, of course, people and people inside. So it's billions of mesh points, and we found that actually opening the windows at least in urban situations, opening windows is not that effective. Very counterintuitive. But rather, putting on strong ventilation, circulatory mechanical ventilation that you have with the aircon in your car is much more effective under low speeds. And I won't go into the details of the physics of this, but basically it's because of we don't get enough pressure difference, and a lot of the air kind of circulates around the window and doesn't really go penetrate inside the cabin under low speeds. And we can do analysis of the nasal system. So we're trying to build an end-to-end model of infection. So in the end, our goal is to, we have a very simple end-to-end model now, but the real goal is to basically do the entire end-to-end modeling of the infection, from what's being the viruses being generated and being mixed up with body fluids, ejected out of your mouth, nose and mouth, spread through the environment. Of course, there are convection with the thermals of the person. So it's a very complicated situation. Then it's absorbed, and of course, kind of sticks to your nasal cavity, but some will penetrate into your lungs. And once it's in your lung, it may attach to the cell. And there are some epidemiological observations and simulations that allow you to predict what the infection rate will be. So, but this kind of end-to-end type of had never been created before. We talked with a lot of epidemiologists, and they said, no, this is like our dream. Okay, so hopefully, so we have a very simplified version of this model. Most of the simulation here is already done, but we also need to do the end-to-end part. But hopefully, we can really contribute to preventing, to really see what the effective countermeasure is, and not rely on simple experiments or hearsay, or even sometimes it's not scientifically well founded things like double masking, which we found to be quite not very effective. Okay, so I think I'm out of time, so I'll stop here. But again, I'll say that Fukaku has been very successful. I'll skip over and go to my last slide, just to take you a glimpse of what to come. So we think that there'll be a disruptive change in 2025 beyond. Our Fukaku successor will be somewhere in the 2028-29 range. So right now, as a research center, and we are investigating all fronts as to what the next machine should look like. And some parts may look like the existing machine, but there will be some disruptive innovations. Hopefully that will drive the IT and the rest of the HPC industry to the new realms in the next generation. Okay, with that, I'd like to end my talk. Thank you very much.
Thank you very much, Professor Matsuoka, for such an illustrating and enlightening talk. We sincerely appreciate your participation in Carla 2021, even more since we know it's midnight in Japan, and you must be very tired. You have left us with many, many interesting ideas to be thinking about for the months to come. I don't know if it would be abusive of us if we may be open for 1 or 2 questions. We're over time, but I know you're very tired. So
please, no. Yeah, well, it's up to you. I'm still awake, so.
Okay, so I'm going to read one of the questions I have. I must tell you, we have many. So if it's okay with you, I'll be sending them through email, and maybe we could get some answers. You could find it interesting. So I have a question about the after Fukaku computing. From your point of view, is it not time to propose non-von Neumann architectures or new post-Moore architectures to achieve a new computing with new performance, thinking in power constraints, performance peaks, new problems, and new software stacks, proposals as quantum computing and others?
Yeah, so So I don't have a slide for that. I have a different slide. So I didn't include it in the stack. Maybe I could just look for it here. Just one moment. Maybe it's here. Yeah, okay. So what I'll do is I'll share this one to answer this question. So we're really thinking, in order to think about what to do next, we really have to, kind of distinguish, what's how the algorithms and the applications will develop. What's the source of speed up, as opposed to saying, no, this architecture is great, or this non-foreigner is great, because those are means to an end, right? So we shouldn't confuse that. A lot of people confuse saying, because computer science, us computer scientists, I'm a computer scientist too, but we always like to kind of come up with clever ideas, fancy ideas, to say this is the next big thing, and try to sell that idea. And of course, it's important to come up with new ideas, but in order to build our machine and set ourselves the right trajectory, that's not the way to go. Because it's the same with going to space. I mean, you can propose various types of new types of engines to travel through space, but a lot of the engines are not very useful, right? Because they're not practical or whatever. So we have to really think about but reaching, let's say, Mars, you have to be very, very pragmatic and think about what are the physical constraints, what are the orbital mechanics, what's the life support. You got to think of all these things for real. Same with computing. So, and we believe, and that's been a little bit introduced at the very beginning, that of course with the Moore's law ending, the flops-centric computing will saturate. Will not end, of course. We always need to compute, but the advances in our ability to have ALUs, to increase the number of LUs with shrinking transistors will end. Although we can put more transistors with 3D, basically we can't use them because the power of the transistor will become constant. So the power, so compute ultimately will become, computing power will be ultimately proportional to the number of the power you use, even no matter what fancy 3D technology or lithography you use, assuming we use CMOS devices. So where do we get the performance? Well, we're thinking there's a big opportunity in data movement, that it being data centric, and not just saying we're going to just support big data. In fact, when you look at this figure, there are lots of algorithms out there, and these are just very small samples. The right-hand side is what Fujitsu gave me as a sample, and said, there are many types of algorithms. They're thinking about all these issues, oh, this is great, let me use it. But I'm saying, no, but you guys don't understand. You don't know the trajectory of these algorithms. What's important, not to think about what's current, but how these algorithms, how on the application side, how these algorithms evolve to make use of the advances in architectural and device technologies. And if we believe that the data will be centric, then what will happen is, from these higher order algorithms, like order n squared, order n cubic, some of the higher polynomial algorithms, or even exponential, some of the low exponential algorithms, they will, work. I mean, there are a lot of work to try to make them into low order, like n log n or order n. For example, neural networks, quantum mechanics. There are, of course, these are right now they're using n cubic and quadratic and n to the fourth, n to the fifth algorithms. But there are a lot of work to make a linear version, sparse version, and so forth. And of course, for things like conjugate gradient, H matrix, and so forth, they are known to be low order. H matrix is making dense, dense matrix sparse, right? So lowering the degree, the complexity. So we believe this trend will continue. And so for this, in order to drive computing, it's not so much think about non-von Neumann. That's a completely wrong thing to say. The right thing to say is, how do we optimize data movement? How do we minimize the data movement, energy of data movement? How do we optimize data movement? Because that's where the bottleneck will be, not the LU. Okay, so how do we come up with the architecture that will minimize these data movements? That's the key. And for so what about quantum? Well, so yeah, we have a quantum institute, we have a quantum computing center now, and we're in very deep collaboration with them. On the other hand, quantum is not very useful for applications that you cannot achieve quantum speed up. They're not, for example, useful for any sort of linear algorithms because they're totally used. Well, they're not. They can do it, but there'll be no point in using quantum computer for linear algorithms. So, so we really have to identify what are the algorithms that can only be solved by quantum, which is basically NP-hard, mostly NP-hard type of problems. Some of the quantum chemistry, cryptography, so forth. But these are not great in number. They're very small in number, although they're very important. So this people having kind of total misunderstanding of quantum computer to overtake standard computing is a complete nonsense, right? Because again, if we believe that the world will become these low order algorithms dominant, quantum computers will have no power there, right? So in essence, we believe it'll be a combination of data-centric architecture, and maybe some architecture could be there, like neuromorphic to kind of bridge the gap between quantum and low order. And then there'll be quantum, of course, to deal with problems that are fundamentally not solvable, unless at least within a reasonable amount of time, because they're NP-hard. So it's really important to think about the fundamentals and not get bogged down by things like this sexy non-Feynman architecture or quantum overtaking everything. Those are completely nonsense. Okay.
So thank you very much for your answer. We're now really out of time. There's many more questions. I know it's very late for you, and we really appreciate your talk. It was a wonderful talk, very interesting talk, and hopefully we will see you soon again. And hopefully we will be in Mexico having a nice drink with us here at home.
Yes, tequila.
Good night. Thank you very, very much. It's been
visit us in Kobe. You'll get to see a wonderful machine. Yes.
Thank you very much.
Thank you.
Thank you.
Thank you very much. Night.
Excellent talk. Thank you very much. Thank you, Professor Satoshi. Thank you for your attention, and we invite you to continue with your connection. You can also follow us. You can also follow the event live on the webpage carla2021.org on our YouTube channel. We now carry on with our next invited speaker, Dr. Jose Mourida, with the talk High Performance Computing with the IBM Power 10 processor. To present our invited speaker, I now give the microphone to Philippe Navot.
Thank you for the introduction. It's my pleasure to introduce Jose Mourida. Jose Mourida is a distinguished research staff member in the Scalable System Department at the Thomas Watson Research Center at IBM. He received a Bachelor Science degree in physics and Bachelor Science and Master Science degree in electrical engineering from the University of São Paulo, Brazil in 1987, 1988, and 1990, respectively. He also received a PhD degree in electrical engineering from the University of Illinois at Urbana-Champaign in 1995. Since joining IBM at the Thomas Watson Research Center, he has worked on a variety of high-performance computing projects. He was system software architect for the Blue Gene supercomputer and chief architect of the commercial scale-out project. He currently leads the IBM research work on the architecture of power processor. He is an author of or co-author of over 100 technical papers and 10 patents. Dr. Mourida is a member of the IEEE Institute and a distinguished scientist of ACM, Association of for Computing Machinery. So please, Jose, let's present your talk. It's a pleasure. Obrigado.
De nada. Thank you, Felipe, for the kind introduction. I also want to thank Isidoro for the opportunity to present my work here at Carla. It's a great pleasure to be here at Carla 2021. The only thing better would be if we were in person. But no, these are not the times that we're living right now. Maybe next year, right, Isidoro?
Next year.
Better luck next year. So yeah, I think everybody could use some real get together with a personal touch. But so today I'm going to be talking about the IBM Power 10 processor, particularly as it fits with in high performance computing. I hope you can see my slides and you can hear me okay.
It's okay. It's perfect.
Okay. All right. Thank you. So the IBM Power 10 processor is, as the name implies, the 10th generation of the IBM Power Systems processor. We've been doing a generation every 3 or 4 years. And I have the pleasure of working for the last 5 years or so from the very initial concept to much of the architecture and design and up to and including the release, the launch of the Power 10 processor, which happened just less than a month ago. It happened in mid-September. So the processor Power 10 is now available. It's designed for commercial applications. But the interesting thing is that commercial applications are becoming, having more and more in common with high performance computing, because there's a lot of what commercial processors do now is analytics. And in analytics, you do a lot of really high compute intensity math operations, whether you're doing graph algorithms or classical machine learning or deep learning for artificial intelligence. Commercial computing, which has typically been associated with kind of databases and transaction processing, those things continue to be important, but more and more they have to do really heavy duty numerical computation for the analytics part. So the Power 10 processor was designed for that. I worked with a lot of people on Power 10 processors. Much of what I'm going to talk here in the first half of the talk is about Power 10 in general. So it's general features of Power 10, many of which I had nothing to do with it. And I'm going to cover more of my own work, which has to do with the new matrix unit of Power 10 in the second half of the talk. So it's a very large team. This doesn't even start to scratch the surface. These are just the people that I work kind of one-on-one with, but there are many, many more people that are involved. Hundreds of people are involved in making Power 10 a reality. So the Power 10 chip, which is the basis of the system. And I'll tell you a little bit about system features, but the chip itself, which is the processor chip, it's a 600 square millimeter, 7 nanometer silicon chip. We organize it has several computing cores. We organize our computing cores either as SMT8 cores or SMT4 cores. An SMT8 core is just a core that can run 8 threads, and it really consists of 2 SMT4 halves. So you can think of the chip, the single chip, as having either a 15 SMT8 cores or 30 SMT4 cores for a total of 120 hardware threads. We actually package this chip as a single chip module, or also as a dual chip module. And if it's a dual chip module, you get 60 SMT4 cores or 240 hardware threads. So a lot of parallelism within a single chip module or a dual chip module. We have very strong connectivity within the chip, and then the chip itself provides a lot of connectivity to other chips in the system. We have a 1 terabyte per second of memory bandwidth through an open memory interface. I'll say a few words about that. We have what we call the power axon interface, which is gives us another terabyte per second to connect to other chips, the non-memory interconnect. And we can build systems. Oops, this must be automatic moving. We can build systems with up to 16 of these chips in a single shared memory image. We have integrated AI acceleration, which is something I worked on myself. I'll talk about it. We have security at all levels of stack, and we really have architected the chip to be efficient from a performance perspective. Up to 3 times the power efficiency of our previous processor, which is Power 9. So we can deliver 3 times the performance at the same, more or less the same power. So how do we you build systems with those chips? Like I said, we have the memory interconnect, an open memory interface with a terabyte per second of bandwidth, which we use to connect to significant amounts of memory, up to 4 terabytes of memory per chip, or 64 terabytes of memory in a system. And then we have the power axon interconnect, which we can use to build either large SMPs or even clusters directly without any additional interconnect. So the power axon interconnect can be used to build large SMPs and also large cluster systems. Can also be used to attach accelerators and things like that. And we have PCIe as well for I/O. So if you go back to the chip that I've showed in this first slide, there is the memory interconnect on the sides, and then the power axon on the corners. That's what I'm showing here. So each one of those, whether you're connecting to memory or connecting to other chips, you have a terabyte per second. So 2 terabytes per second total. Really give you maximum connectivity to memory and to other components of the system. The memory interconnect is a new interconnect. It's this open memory interface. It is indeed an open memory standard, but it's not the usual, let's say, the DDR standard that people see. So our memory chips actually have our memory modules actually have a buffer chip, which does the interface between our open memory interface standard and what the DRAM chips actually speak, which is, in the current case, DDR4. In the future, it can be DDR5. So like I said before, you can have up to 4 terabytes of memory in one socket, meaning it really, this terabyte per second of total bandwidth is actually over 16 channels. So on each channel, you can plug one of these memory cards, and they can be 256 gigabytes, so 4 terabytes total per socket. If you build a system with 16 sockets, that's how you get 64 terabytes. So really, as you can see, this chip is meant to be used in systems of up to very significant size and very significant memory capacity to solve very large problems, even on one single memory image. And then we can cluster. I'll tell a little bit more about the clustering technologies. So this is what the DIMM, our memory card looks like. The normal memory card that you see on a server is here in the bottom left, and it's a DIMM with memory cards, and the interface that go over the pins is the usual DDR4 memory memory interface. We used to have in previous systems our own memory cards, which had a very large buffer chip here under the heatsink. You can see the chip, which did a conversion of protocol between our proprietary protocol and what the memory speaks. And we have essentially merged these two technologies in our new open memory interface card, which is a much smaller card. This is more or less to scale. It has a very small from number of pins interface, but very fast. It runs at 30 gigatransfers per second, and it can run faster in the future. That's the open memory interface. And then there is a small buffer chip which converts that open memory interface to the DDR4 interface that the memory chips actually talk. So it's technology agnostic. We can replace this DDR because really what the card is talking is the open memory interface. This buffer chip does the conversion, so a different buffer chip can convert to DDR5 or GDDR or whatever HBM or whatever really we want to do. This is technology agnostic. It's low cost, gives very large density and very large capacity with low latency and high bandwidth. So really, it's kind of what we were going for with the open memory interface is the combination of very high bandwidth, kind of 1 terabyte per second. It really is as the kind of an HBM-like bandwidth, but also very high capacity, 4 terabytes of capacity per socket is so high capacity and high bandwidth. So that's the open memory interface side of the interconnect, but with the power axon, we can also use the interconnect, the chip interconnect to connect up to 16 of the single chip modules together, forming a 16 chip module shared memory system. So that's if we focus on single chip. So I said that we can use single chip modules, which have a very high thread performance. The chip can run up to 4 gigahertz. And it has up to 15 SMT8 cores or 30 SMT4 cores, but the important thing is 120 hardware threads can execute at the same time, and you get all the memory, which is essentially a terabyte per second, down to a single chip. We also build dual chip modules, so it's twice the amount of silicon in one module. This is becoming more and more common in the industry. AMD processors already are multi-chip modules. Some of Intel processors are dual chip modules, and Sapphire Rapids, which comes out next year, I believe, will be quad chip modules. So we have dual chip modules, which has twice the number of cores, but they can't run as fast because that would exceed our power budget. So we can run up to more or less 3.5 gigahertz, but still it's a significant improvement in throughput. So it's a lot more throughput, but you lose some of the thread performance because you have to run each thread slower. And we can build systems with up to 4 of these sockets. So this would be kind of our high density, high throughput system that then you build, you scale out, while the one on the top is kind of the single system image, very large capacity. A new feature that Power 10 introduces is memory inception. What memory inception lets us do is share memory across systems. So you can have, in this case, it's a cluster of 8 systems. Each one is a shared memory box. It runs its own operating system. It's a single image system, is each one of these. So there are 8 of those, but they can cooperatively share the memory so that applications running on one system can use the memory on another system. So in this case, I'm showing there's a certain workload A that is running on the first machine, and it only uses memory on that machine. Now, workload B needs a lot of memory. It cannot possibly fit all the memory that it needs on one system. So what it does, it borrows memory from other systems. So it borrows memory from the first system here. You can see about half of the memory is being used by workload B, and you can see workload B running on, workload B runs on one system, but it uses the memory of several other systems. And in fact, it doesn't use any memory in its own system, which is not something that, may not want to do it, but you can do it. Is that you can run completely out of your own system memory. So because from a processor perspective, you are just doing loads and stores against a memory address space, and that address space spans several systems. We can actually build address spaces of up to 2 petabytes. So you could have a single application. The application itself would run on one system, but accessing 2 petabytes of memory. And with a little bit of care, you could have 2 applications sharing memory. It's not really meant to be cache coherent shared memory, so there's a lot of care has to be taken if applications want to share the actual memory. But it's really meant more as a way to disaggregate processing and memory, so that a single application can use much more memory than it fits on a single system, or while other applications are using memory local to its system, and some applications, like application C, is using both local memory and memory in other systems. Okay, so it really gives us the flexibility to scale our problem to something that you can't realize on a single machine. We really work hard to deliver a lot more performance over our previous processor. So Power 9 was the machine that preceded Power 10. I had the privilege of working on Power 9 as well. And the Power 10 performance tends to be, module to module about 3 times the performance of Power 9. So we increase the general workload speed up is 3x. A lot of it is because we have more cores. Power 9 was limited to 24 cores per socket. In Power 10, we can have up to 60 with a dual chip module, so it's that by itself is 2.5, but then the cores themselves are also faster, and our memory speed is memory throughput is also higher, depending whether it's DDR4 or DDR5. DDR5 will eventually be 2 times faster bandwidth than DDR4, using the same channels as just a new memory card. On certain applications that are matrix computing heavy, we actually saw a lot bigger performance improvement over Power 9. So for example, in LIMPAC, which I'll talk a little bit more, we are 10 times faster on certain inference computations, like ResNet 50, done in single precision floating point. We're also 10 times faster. If we go to lower precisions, we can actually be 20 times faster or more than our previous processor. This big gain in performance for matrix-based computations is because of a whole new unit in Power 10, which is the matrix math assist unit. It's the unit that I worked on, which does matrix computations much faster than they could be done otherwise. So that's the reason for the big 10x gain for these matrix heavy operations. So 3x in general, 10x on the matrix heavy operations. So let me talk a little bit about the Power 10 core, which is the execution engine that really was greatly improved over Power 9. That gives us the performance improvement in terms of efficiency, and also in terms of raw performance. And it has significant, it has this new matrix accelerator, the matrix unit that I talked about, but it also has a lot more vector processing, has 2 times the vector processing of Power 9, has 2 times the load store bandwidth of Power 9, and have 4 times the level 2 cache of Power 9. So all these gains really resulted in essentially a 3x performance improvement, which in terms of power efficiencies was a 2.6x performance per watt, because it has 30% average core performance improvement, 50% average core power reduction, and then the core also runs faster. So that's why, then it runs a little bit more, consumes a little bit more power. So that's why the performance is 3x and the performance per watt is 2.6x. So the core, the Power 10 core microarchitecture, this shown, this is an SMT4 core. The SMT8 is just two of these. And what you can see here is right in the middle are the execution slices, are really the functional units that execute scalar and vector instructions. These are 128-bit wide pipelines, so we can produce 4 128-bit results per cycle. And these are complemented by the matrix unit, which can produce 2 512-bit results per cycle. And I'll talk more about the matrix unit in a moment. The L2 cache was the big thing, another big thing that we changed is the whole megabyte cache. The rest is kind of incremental gains. The L1 data cache is the same. The L1 instruction cache is a little bigger. But that's the essence. So let's talk a little bit about the matrix unit. The matrix unit is a new feature of Power 10. It was not available in Power 9, and in fact, Power 10 is the first commercial processor with a matrix unit. It won't be the last. You'll be seeing matrix units come in other processors next year. Some from IBM, some from Intel, and I imagine AMD cannot be that far behind. ARM also has announced matrix units. So matrix units are things that are coming. We had the privilege of being the first commercial processor to have a matrix unit. And what a matrix unit does, it does, as you can imagine, matrix operations. So in the case of Power 10, we have a matrix unit which uses two vectors, in this case shown an X vector and a Y vector. And it does a matrix operation, which takes each element of the X vector and multiply by all the elements of the Y vector. So it's an n square operation, right? If you have n elements here, you have n elements there. You can do n square operations, and you update a small, in this case, a 4x4 matrix, which is stored in a matrix register. So these are vector registers, X and Y, doing a matrix operation that updates a matrix register. And this is done on the matrix unit. For those that are familiar with BLAS, this is what's called a BLAS2 rank 1 update. It's a GUR instruction. It takes two vector XY, computes XY transpose, and adds to a matrix A and stores in the same matrix A, updates the matrix A with the sum of the outer product of X and Y with the original value of matrix A. This can be, the way I've shown here, this works for single precision numbers. This is the 32-bit numbers. We have 128-bit vectors. So you have 4 single precision numbers per vector. So 4 elements, you update 16 elements on the matrix. You can also do reduced precision data types. If you have a 128-bit vector register with 16-bit elements, really what you have are 2 4-element vectors, each of 16-bit elements, and you do multiple rank 1 updates, or you do what's called a rank 2 updates. So in general, it's the operation that we perform the matrix units is a rank K update, which can be exploited by a variety of computational kernels, BLAS3 and BLAS2 kernels, sparse matrix operations that we have done, direct convolution, discrete Fourier transform, and stencil computations are all operations, all computations can be expressed as these rank K updates. I mentioned that the small matrices, the 4x4 matrices, are stored in matrix registers. So we have created a new set of 8 registers that we call accumulators. So we have 8 accumulators in the Power 10, each one able to store a 4x4 matrix of 32-bit elements. I'll talk about 64-bit later. The vector scalar registers are 128-bit wide. So the instructions always take 2 vectors and 1 matrix, and they do the outer product and they update the matrix. In the Power 10, there is a, this is something we did more to support system software. If you're using accumulators, it kind of blocks the corresponding vector registers. So if you're using all 8 accumulators, you cannot use the first 32 vector registers, but we have 64. So you can always use, so the vector register continues, 32 to 63. Those are always available and the first 32 vector registers, when you use an accumulator, you block 4 of those. But think of the accumulators as being matrix registers and the vector registers as being no vector registers. So again, just what the operation is for 32-bit is what I showed before. You have 2 vector register inputs, each one has 4 element vectors. You do the outer product, and you update a 4x4 matrix of 32-bit elements. So that's a rank 1 update. You can do multiple of those. Each instruction will do one, but if you do a series of those, you can do a computation like a matrix multiply or a convolution, whatever you want that is updating this 4x4 matrix. Now, what if I had, here in more detail, what if my elements are 16 bits? Well, if you have 128-bit vector registers and your elements are 16, really think of this vector register as being 2 vectors of 4 elements or a 4x2 matrix of 16-bit elements. So now you do a rank 2 update, you multiply a 4x2 matrix by a 2x4 matrix, which produces a 4x4 matrix, and with that you update the matrix register. We can do 8-bit elements, so in this case each vector register is a 4x4 matrix of 8-bit elements, updating a 4x4 matrix of 32-bit elements, a rank 4 update, and we even can do 4-bit elements. We can do a rank 8 update in a single instruction. So these are the instructions. That's what the hardware can do, and then the software builds from that. So for integer data, the operations are outer product plus store plus add to the current value of an accumulator. For floating point, we actually have the option of negating the outer product and negating the matrix before we do the update. These are all very useful when you do certain operations in LIMPAC. For example, you actually take the outer product and you want to subtract from the current value. So we can do that. So the compiler support is somewhat limited today. Really what we have is in the compiler a set of built-ins, which is a standard feature of GCC and LLVM compilers. And the built-ins are essentially equivalent to a assembly instruction. So you program with built-ins. The compiler will translate those built-ins into instructions, but it will also do the register scheduling, the instruction scheduling. You don't have to worry about the details of what are the registers number, what are the accumulators number. So it's far more portable than programming directly in assembly, even though it seems to be more or less the same level of abstraction. So how do we write something like a real computation using these built-ins or these instructions? Essentially, the built-ins map one-to-one to the hardware instructions. Well, so here what I have is a simple DGEMM microkernel. So a DGEMM microkernel is something that computes a panel, a small panel, in this case an 8x8 panel of the result, by multiplying an 8x(n) panel of one input by an n/8 panel of the other input, right? So it takes 2 inputs, x and y, does the matrix multiply, and updates an 8x8 panel of the result. So because the input x is seen as a collection of 8 element columns, okay, and y is a collection of 8 element rows, I'm going to read 1 column of x, 1 row of y, do the outer product, and update the 8x8 panel. And I will do that n times, so that in the end I have completed the matrix multiply. So that's why you see here the outermost loop is a loop from 0 to n-1. I'm walking the columns of x and the rows of y in each iteration of the loop. So I fetch, and x is my vectors of will be the x0 and x1 together will be 1 column of x. y0, y1, y2, y3 together will be 1 row of y. Why do I do this? Something that seems strange here. I use two 4-element vectors for the column and 4 2-element vectors for the rows? Well, because in double precision, the accumulator actually has this funny 4x2 shape, right? Because the accumulator is 512 bits. So if my elements are 64-bit, I can only fit 8 elements, and the way I fit is a 4x2. So the 512 bits of the accumulator really represent a 4x2 matrix of double precision. And if I have a 4x2 matrix as my accumulator, I need to multiply a 4-element column by a 2-element row to update that accumulator. I have 8 accumulators, so each one is 4x2. So the kind of the virtual accumulator that I build is 8x8. So it takes 8 instructions, 1, 2, 3, 4, 5, 6, 7, 8, each instructions, each one updating one accumulator to one architected accumulator 4x2 to produce the virtual 8x8 accumulator. And the x0, x1, y0, y1, y2, y3 are the inputs. So these are just vectors. I just read with no, I just read from memory using no pointer dereferencing here. The compiler will translate to vector load instructions. And then I use the built-ins to actually do the outer products of the vectors that I read and update the accumulator. So this is all it takes to write a DGEMM microkernel in using these instructions. This is the code generated. I mean, this is the code in C that I actually wrote. This is the code in assembly, and you can see essentially a one-to-one translation. The built-ins that do the outer products. You can see here DX, VF, 64, GRP. This is no a complicated number, but a complicated name, but there's a logic behind the methods. They get translated to 8 machine instructions, and the dereferences to the pointers for the X vectors X0, X1, Y0, Y1, Y2, Y3. They get translated into load instructions, and then these adds are just advancing the pointers. And then I loop back. No, this is a branch back to here. So each iteration of this loop will do an outer product of an 8-element column by an 8-element row, and update the accumulator, and then I repeat n times to complete the matrix multiply. Is the Power 10 with the matrix unit fast? Yes, it is. So the peak performance is 32 double precision flops per cycle. And here you can see for different problem sizes, I'm doing a matrix multiply. I get about 26 out of 32. I think we can actually get a little bit more than that now, maybe 28 out of 32. So about 90% of peak is possible. This is with the matrix unit. The orange bars represent what Power 10 can do without the matrix unit, and the green bars what Power 9 could do. So a significant gain, about 5x gain in performance on matrix computations from Power 9 to Power 10. LIMPAC is also pretty good. The performance of LIMPAC is very sensitive to the problem size. You can see here the performance in flops per cycle for a single thread. As the problem size grows, the performance grows, and again the performance with the matrix unit is about twice without the matrix unit, and about 4 times the performance of Power 9. For a big enough problem size, as shown here in the bottom, to about 250,000 unknowns, LIMPAC can achieve this number of gigaflops, which is 2,905 gigaflops. That's a single chip module. Just one chip of Power 10, getting almost 3 teraflops on LIMPAC. And to our knowledge, this is the best single chip performance ever for a CPU. I mean, I should, of course, know GPUs can do more than that, but for a CPU, this is really the best performance that we know of for a single chip. No, maybe there are other things that we don't know that can do better, and we know there are the dual chip modules that are better than this, and our own dual chip module will be better than this as well. So for a single chip module, this is almost 3 teraflops. Problem of size, of course, this is a big problem size, and you can do because the system can fit a lot of memory, right? We can have up to 4 terabytes of memory on a single chip. This uses about half a terabyte of memory. A little bit less than half a terabyte. So we could do even big problem sizes. So I already mentioned the advantage in flops per cycle over Power 9. So Power 9 was 1 Power 10 will get about more than 5 times the performance per cycle for these matrix computations. But the best part is that actually does that with less power. So the MMA is very power efficient. It does a lot more performance, 5 times the performance at less power. And why does it do that? Because there's less data movement, right? Yes, it's a newer technology, all that helps. But no, we go back to the first slide that I showed on the matrix unit. We fetch only 2 vectors. And by fetching 2 vectors, I can do 2 4-element vectors or 2 n-element vectors. I can do n square operations. So it's n square operations with n data. It's that really intensity of operations versus data that really allows it to be a very power efficient. And our matrix unit is very power efficient. We have been working on using the application that I showed here, matrix multiply, is kind of a natural fit. It's the first thing you think of when you think of a matrix unit. But we want to see, can we use our matrix unit to do sparse matrix computations, which may seem a little more difficult. And yes, it is, but it can be done. So we've been working with a student, Sharif Yassil from University of Illinois at Urbana-Champaign, and he developed a process by which he takes a sparse matrix and decomposes into 2 different parts. One part of the matrix is blocked. It has dense blocks, which can then take advantage of the matrix unit, and a more sparse part, which can't take advantage of the matrix units and therefore executes on the vector unit. So essentially, he decomposes a sparse matrix into a blocked matrix that fits the matrix units and a sparse part that fits into the vector units. And with that, he gets very good speed ups. It's not for every matrix. Some matrices, so here's a graph of speed up over a normal CSR computation using only vector units. So some matrices, the matrices on the left, you don't get much speed up. You can see 1 here, meaning there's not much speed up from his technique. But then you have a whole class of matrices where you get significant speed up from using these matrix units. Some of them get 2x, 2.5x performance improvement by splitting into a kind of blocked part and a sparse part and letting the block part run on the matrix unit. And in fact, for some matrices, we get over a teraflop of performance on sparse matrix computation, which is very significant, right? We get a little bit less than 3 on LIMPAC, and we get more than 1 on a sparse matrix computation. So a sparse matrix computation is effectively getting 40% of the LIMPAC performance. The sparse matrix computation here is sparse matrix multiply. So sparse matrix times a dense matrix multiply for the dense matrix having 128 columns. So we're very happy to see this significant boost in performance on sparse matrix computations as well from our matrix unit. So let me come to a conclusion and leave some time for questions. Power 10 is the latest generation of power systems processors for enterprise computing. We saw a big improvement in compute, memory, and interconnect over our previous processor, Power 9. We have 3 times more socket performance. Sometimes when the computation is matrix heavy, we have 10 times more socket performance. We really are very proud of this new facility to be the first processors out there with a matrix unit, which directly implements matrix operations in hardware and can give a significant boost in performance. So we have been able to achieve new levels of performance on the things that we expected, like dense linear algebra, but we're also now exploring other more challenging spaces like sparse matrix computations. Power 10 is out. Is a machine that is commercially available. But if you just want to play with it, you can play on any machine. You can download the IBM Advanced Toolchain, which is a cross-compiler. Now you can download it on a Power machine that you have, or you can download it on an x86 machine, and it will generate code for Power 10 systems. So you can try the IBM Advanced Toolchain on your own computer, and then hopefully we can have access to Power 10 systems soon. We're looking on that. And you can also try the functional simulator, so you can also run the code that you produce with the compiler. So with that, in the interest of leaving time for questions, let me pause here and thank everybody for your attention.
Thank you, Jose Mourida. Thank you for your
Felipe.
nice presentation. We are waiting for some questions. I had a question. I was very curious. Why you decide in the study of the power 10 to put in hardware this matrix multiplication? Yes. What kind of study the IBM do, considering that is an important function to put in hardware?
Well, so the really it was the it was the way we found to significantly boost our performance within the power budget and the area budget that we had. Now, every time you design a processor, you work with a power budget, how many watts you can burn, and then you have an area budget, how many square millimeters of silicon we have. And the matrix operations, particularly this outer product operation, is efficient on both. It's efficient on area and it's efficient on power. Why is that? Because you are using a relatively small amount of input. You're using just 2 vector inputs. This is 128-bit on X, 128-bit on Y, and yet you can produce an amount of computation that is quadratic. You can produce 16 multiply adds per cycle. So you can pack and all that is concentrated in one unit, right? So you can pack a lot of computing power in a unit, in the matrix unit, and you can bring relatively small amount of data from the vector registers to that unit to do that computation. And a lot of power goes into transferring data. And because we transfer little data, now the matrices reside in the unit, right? The matrix, you may say, oh, this is 128 bits, this is 128 bits, but the matrix is 512 bits. And yes, it is, but the matrix stays in the matrix unit. So the matrix is local to the matrix units, doesn't have to be moved. Only the vectors have to be moved, so it's a lot less movement. So for example, if we were to do this in a vector operation, this vector X would have to be 512 bits, the vector Y would have to be 512 bits, and the matrix A would be 512 bits, everybody coming from vector registers. So I would have to transfer 1500 bits of data to do one operation. Here I transfer 256. So it's much less data movement for the same amount of computation with much smaller vectors. So it's a more efficient way to get that. Now, there are things that, this is a matrix unit. There are things that a vector unit does better. We still have our vector units. In fact, we have 4, which is more than Power 9 did. So it's not like this is all we did. I mean, we boosted our vector performance and we introduced our matrix units.
Very nice. Yeah. I understand that the data movement was one of the reasons of that. There is a lot of questions here. Let's see. From Carlos Barrios, there is, for this kind of processor, it's not necessary another kind of memory, and the problem of cache coherence is still.
No, we don't need another kind of memory. I mean, we did another kind of memory interface because we wanted the bandwidth, right? So if we were to get a terabyte per second out of the standard DDR4 channels, we would have to put too many channels. We wouldn't have enough pins on the chip to support that many channels. So we designed our own, well, it's our own, but it's a standard now. It's an open standard, the open memory interface, which is a high frequency, 32 gigatransfers per second, narrow interface. So we can put a lot of them in the same chip, right? We can put 16. So let me get the drawing here. This may be so. Oops. So in one chip, we have 4 these corners. Talk about the memory. So in one chip, we have two of these open memory edges, each one with 8 interfaces. So we have 16 memory interfaces on a single chip running at 32 gigatransfers per second. So they can't be very wide. It has 6 times the bandwidth per area compared to DDR4. So we would never be able to get this much bandwidth out of DDR4. So we have a lot more bandwidth out of the chip using our own interface. But then we want to use normal memory, common memory. So then we put the buffer chip on the other end, which translates the open memory interface to the DDR4 interface. So the memory is industry standard. It's a DDR4 memory. The channel that goes from processor to memory is a new technology. Hopefully that answers. I don't know if that was the question.
Okay, no, I think so. There's another question from Maria Ruiz Varela. Could you comment on IBM roadmap and plans for delivering HPC leadership class system with Power 10?
Oh, I could comment on anything, and yet it would be wrong because I don't do roadmaps and things like that, right? I develop processors. What people do with roadmaps, it's somebody way above my pay grade decides what to do with them. So I design processors, and I think we designed a very nice processor for HPC. And now it's a question of, are we going to actually build some large systems with it? And I think all I would say is that we are a company, and if somebody pays, we will do it. And if nobody pays, we won't do it. So I think the problem, no, it's a matter now of finding customers that are interested in building large systems with Power 10. There has been some signs of interest. Like I said, I think there has been a convergence between business processing and HPC processing thanks to all this area of analytics. Now, in analytics, we have to do heavy computation, we solve systems, we do matrix operations, and we end up building a system that is good for commercial computing and for the more traditional HPC, the physical simulation and all that. And now it's a matter of finding interested parties to work together. The memory inception also is another great feature, right? It's not normally what you think from HPC because you think more of clustering techniques. But no, the fact that you can have a system using memory of other systems, I think that opens a lot of opportunity for HPC. You can solve much larger problems than you could otherwise.
Did you see there is another question here about worldwide? How many HPC implementations do you calculate IBM has? And what is the largest or most important? I think he's asking about the Summit machines.
Yeah, the largest and most important are the Summit and Sierra, right? Which are currently number 2 and 3 in the top 500. Those Power 9 systems, they are Power 9 systems with GPUs, and they are, for a while, Summit was number 1, and then until Fukaku, who Satoshi gave the most amazing talk. I'm sure he went to sleep, but I already sent him a congratulatory email. I thought that was an amazing talk about Fukaku, and Fukaku really now is number 1, and there's but for a while, Summit was number 1. And it was a very large system. I don't know how many in the top 500 currently are IBM. I would have to count. We don't have any Power 10 yet. Power 10 is just came out.
This is an interesting question. There is a project for a machine with the Department of Energy with Power 10.
Not that I know of. I mean, like I said, Power 10 just came out. Came out last month. I mean, 2 weeks ago, maybe 3 weeks ago. So yeah. So I think it's too early to say. Yeah, we need more time to do something with it. So.
Very nice, very nice. Okay, I think we are Satoshi takes
way above time, but it was.
We are 10 minutes more now. So,
but it was.
Thank you very much.
Thank you.
Thank you to presenting a very nice talk about the new processor, and I hope see you again another time in another conference.
Yes,
you,
in
Jose
person.
Thank you for the organization of Carla.
Thank you, Felipe. This was great. Thank you.
Thank you. Gracias. Obrigado. Bye-bye.
De nada. Ciao.
Ciao.
Great talk. Many thanks for staying with us. You can also continue to follow us on YouTube. And with this, the morning events are almost concluded. But now we invite you to continue the conference on a different room on Zoom. The tracks room is now habilitated and the link will be shared in the Zoom chat in this moment. And you can also see the link on the webpage of the conference. We warmly welcome you to return to this main room at 1 p.m. Mexico City time to continue with our special conference by the University of Guadalajara. See you then.